In this video, you're going to learn how to code and install into your car my number plate recognition system from this video using the Asus Tinker Edge T.
This is a system you can code and hardwire into your vehicle. Look, there's a camera mounted on the grille, there's the Asus Tinker Edge T, a monitor in the car, and it actually works, despite being inaccurate sometimes. What I've basically created here is a highway patrol police car. I mean, even Teslas can't do this. Now, my system that you'll be learning to code today is called the Automatic Number Plate Analysis Legend, or ANAL for short. What it basically does is use deep learning AI to detect the license plates, convert it to text, and return the results onto the screen. So now that you know what it looks like, let's have a look at what hardware and software we need.
First off, we'll need an Asus Tinker Edge T with a power supply and HDMI cable, a USB camera, and a PC. Then for software, on your Tinker Edge T, you'll need the latest operating system, which is Mendel 5 at the time of recording, Chromium and Jupyter Notebook installed from pre-built binaries, and have OpenCV, Tesseract OCR, and OpenALPR built from source. We can't use any of the pre-built binaries for the last three items, and if you're not sure how to install any of them, I've got tutorials on all of that. Links will be in the video description. And for your PC, you'll need Python 3.9 installed. At the time of recording, Python 3.10 was the latest, but wasn't compatible with the next step, which is creating the GUI. You can try with Python 3.10, maybe it's fixed by now, but I'll let you know where Python 3.10 didn't work as we keep going. Now that you've got all the hardware and software, let's hop on the PC and start this project. So the first step is to create our GUI, and we're going to make that using PyQT5, which is a toolkit for creating cross-platform GUIs. So on your PC, we'll open up a terminal and we'll install PyQT5 with pip install PyQT5. I've already got mine installed, so yours might take a bit longer. Once that's done, we'll install PyQT5 tools. So that'll be pip install PyQT5-tools. Again, mine's installed, so yours will take a bit longer. Once that is installed, we'll then open up our GUI designer by going to your Python-based directory. By default, it should be in C program files Python 39, but I installed Python straight onto my C drive. So I'll click in here, and then we'll go to lib, site packages, Qt5 applications, Qt, bin, and designer. Now, designer is a GUI for creating GUIs. Sounds like a worthy exhibit meme right there. We use designer to drag and drop widgets like text boxes, scroll bars, and buttons to create a GUI, which I think is much easier and faster than coding a GUI from scratch. Now let's set up the main window. If you didn't get this pop-up at the start, then you can go to File, New, and we'll select Main Window and click Create. Next, we'll set the geometry or the window size here to be 840 by 480. We won't need the full 1080p size for our Tinker Edge T. And then we're going to add a label, which will be the container for our webcam video. Sounds kind of weird to call it a label, but I think it's like an image label or an image container. And we're going to call it img label because I have no creativity. You can call it whatever you want though. And then we'll just adjust the X and Y, the width and height, so that will be 0, 0. And our webcam feed is going to be 640 by 480. Next, we'll add a table widget. And we'll drag that in. And so the X and Y coordinate for this is going to be 640 at Y0. And the width of this will be 200, so we can get it just right on the edge of the screen. And the height for this will be 480. We can remove the menu bar at the top here because we won't need it. And then we can probably rename our window to something more appropriate. Right now it says just main window, but we'll choose something like ANAL because that's the name of our application. All right, cool. I think we're done with our GUI here. So let's just save it with Control S and we'll call it GUI.UI. Now we need to convert this UI file into Python code so we can use it in our Python script. You can use this form view Python code feature in PyQT5, but you'll run into issues later when we execute it in our Tinker Edge T. So instead, what we'll do is go back to our terminal, and we're going to use this PyQT5 help command to generate our Python code. Make sure you're in the same folder as your GUI.UI. So I'll just quickly change directories there. And then we're going to type in PyQT5-x GUI.UI output GUI.py. This is where it wasn't compatible with Python 3.10. Hopefully that's created the py file, and when we run it in idle, hooray, we've got our GUI window. The next step is to add an OpenCV webcam into our app, specifically into IMG label. Now, I'm going to be straight with you here. I copied someone else's code for this because I hate GUI programming and integrating stuff with GUIs. It's boring, it's tedious, and I'd rather get hit by Mike Tyson than do GUIs. I mean, I'd probably die, but at least I won't have to code GUIs ever again, right? So in saying all that, this is the slab of code that I copied from Stack Overflow. And this is great because this piece of code does exactly what we need, which is to create a Qt application with Q-threading included. This means that one thread will be used for providing the webcam feed, and I believe the other thread will be used for everything else. In our case, it's going to be, converting the plate to text and displaying that text on screen. And the reason that's important is because the CPU in the Tinker Edge T isn't as fast as what you'd expect from a desktop, so we need as much optimization as we can get, which is what threading helps us with. Now, let me try to quickly break down what's happening with this code. This UI main window class is the GUI, and we're going to copy the contents of our GUI.py file into this class here. And then this framed grabber class at the top is where we're going to write all our code. And you can see that this is inherited from the qtcore.qtthread class. And then this block of code here, this def run, adds an OpenCV webcam feed. And according to the Qt documentation, this run function, when used with a Qt thread, starts an event loop inside the thread, so it sounds like this loop will keep going on and on and on. And then coming back to this last part here, signal.emit, I'm not 100% sure about it, but I think it lets you pass like an image or a variable, which is this here, into a different class. So we can see that we're doing signal.emit image, and we're going to pass that into the other class here, and in update frame, we can see that we're calling image there as well. If someone could confirm that, that'd be great. So let's copy this slab of code into idle. We'll paste that in, and we'll call our new script ANAL. We'll probably just put that into our C drive. Fantastic. And then we've got to copy this main.py file. I don't think we need to create a new file for this, so I reckon we can just copy this and put it straight at the bottom of our anal.py script. And we probably won't need this first import, so we can remove that. So we'll just run this again to make sure the webcam's working. I had to turn mine off because I was, already using it. Now, if your video is not loading, there's two things to keep in mind. The first is that it can take up to 30 seconds for your webcam to load. If it's still not loading after 30 seconds, then what you'll have to do is go to a bit further up in this script and update the video capture index here from 0 to 1. Mine was connected to index 1 instead of index 0. You'll have to keep going up the numbers if 1 didn't work. You can try number 2, 3, and so on. So we'll give that a go now. Yep, and awesome, there I am. Let's close this. Next, we're going to copy the code from our GUI.py file, which is this one here, and we're going to paste it into our ANPR script, specifically the setup UI and the retranslate UI functions. Let's start with retranslate UI because I think that's the easiest. So let's open this up side by side, and we'll copy this in and paste it in there. Now we'll do setup.ui. So that's all that. And we'll paste it here. And then for update frame, we'll change this webcam display to IMG label because that's what we're using to house our video feed. Let's just save and run this to check that it's still working. And awesome, we've got video, but you can see that I'm kind of off the frame here because the resolution is too big for our UI. So let's change the video resolution. We'll close this first. So we'll go back up and change the video resolution up here. So the first one is height, so that'll be 480, and this one, which is the width, will be 640. Let's just quickly launch it again. And awesome, that looks like it's working now. So we'll close this up. The last thing we have to do before we move on to the next step is coding the exit function under update frame. So what we'll do is we can probably replace this since we don't use it anymore, and we'll call this app execute, and this will be self.grabber.app execute. If we don't add this code, I believe the frame grabber class will keep running in the background even after we've exited our application, which we don't want. And then actually we can remove this line here because this is what's causing the text label to appear every time we launch our app. So we'll delete that and save it. Now, just to reiterate, the reason we're taking this code from Stack Overflow is because this has the OpenCV code we need, which I don't know how to do, and then we're just putting our own GUI on top of it. So now that we have the video from our webcam, let's quickly put the rows and columns onto the table because right now it's empty. So what we'll do is update this set column count to 3 and set row count to 15. I think that's pretty generous. And the reason I have 3 columns is because the results from my government website shows if the plate, which will be column 1, has any fines, column 2, or sanctions, column 3. And that's all I need to know. The plates, the fines, and the sanctions. And 15 rows because I think that's a generous amount of rows or plates to show. So we'll save and run that. And awesome, we've kind of got our 3 columns here, but they're a bit too big. So let's fix that. And we also don't have column headers. So just over here, we'll type in self.tablewidget.set horizontal header labels. And I'll call mine plate, rego or registration, and sanctions. And then to resize the table to fit within that space, we'll use self.tablewidget.horizontal header.set section resize mode 0 qt widgets.q header view .stretch. And if we paste that 2 more times, but updating the column index number, and then changing this to resize to contents instead, that should fix everything. So we'll just double check that works. Awesome, yep, that looks like a really snug fit. Once again, I just have to say thank you to RoboMatt here for this post. It honestly saved me from Mike Tyson. I'll leave a link to this page in the video description too. So now that we have a working interface, it's time to transfer this to our Tinker Edge T. So plug that into your Windows machine, and we're going to use SSH for this. If you haven't set that up, then follow my SSH tutorial and then come back here. So in your terminal, we'll go to where our ANPR.py script is, which is in cd C drive ANAL, and then we'll type in mdt push anal anal.py. Cool, that's pushed our script across, and we can check that with mdt shell. And there it is, albeit with some extra characters, but we'll fix that in a sec. Okay, so we're pretty much done with our Windows machine, and from here on out, we're only going to be working with the Tinker Edge T, so let's switch displays. Now the file would have been copied to home Mendel, so let's open it up there. And let's fix up the file names by renaming our Python script with sudo move home Mendel anal.py, and we're just going to call that anal.py. And we'll remove that extra folder with sudo rmr home Mendel. If you can hear a fan whirring in the background, that's the Asus Tinker Edge T. Next, plug in a webcam to your Tinker Edge T. I've got to disconnect my webcam and put it into the Tinker Edge, so that's the end of me. And then we'll run our anal script with sudo python3 anal.py. Now, if you get this xdisplay error, it means you'll need to install xorg with sudo apt-get install xorg. If you've already got it, then every time you boot into your OS and run this script, you'll need to type out xhost space local root. You don't need to do this every time you run your script, just every time you boot into the OS and want to run your script. So we'll try to run our script again with sudo python3 anal.py. And awesome, that seems to have loaded our GUI. Now, if you get a module not found error, like a no module named PyQT5, it means you need to install PyQT5. And thankfully, you can just use the pre-built binaries. So we'll install it with sudo apt-get install python3-pyqt5. I've already got it installed, so yours will take a bit longer to get through this step. Then you can run your script again. And the last problem you might have is that there's no video, even after waiting 30 seconds. And that's usually because our Python script is looking up the wrong USB port or camera index for our webcam. But we can update that easily inside our Python script. So we'll sudo nano anal.py, and we'll just make this a little bit bigger. And see this video capture 1 here. Depending on which USB port you've plugged your webcam into, it'll be index 0, 1, or 2. I've plugged my webcam to the top USB port, which is index 2. So I'll change that to 2, and the bottom USB port should be index 1. So we'll exit with Control X, press Y to save, and press Enter. And we'll run our script one more time, and hopefully we get our video pretty soon. And we're still getting an error. Hopefully this is the last one. So it says attribute error, type object, Q image has no attribute, format BGR 888. This is an easy fix. So we'll sudo nano back into our script again. And line 19 is where the culprit is. Now we can see the code that we took from Stack Overflow is using the BGR color format, but it doesn't exist for PyQT5, I think. Now we still need to use BGR, so what we'll do instead is update this to RGB 888, and then according to the Qt5 documentation, there's a QImage function called RGB swapped that converts it from RGB to BGR. So we'll add that in. And this converts it from RGB to BGR. So we'll save that, or close it with Control X and save with Y. And we'll run it again. And ta-da, we have our video working. How cool is that? We'll close this. The next thing we'll want to do is add object detection to our app. And the easiest way to do that is by copying the OpenCV object detection code from the Google Coral Examples camera project on GitHub. Now, the reason this page is relevant is because the Tinker Edge T uses the Google Coral TPU to accelerate deep learning, so a lot of the Google Coral projects can be used on the Tinker Edge T. So let's clone the GitHub repo with sudo git clone https github.com/Google Coral /examples-camera. I've already downloaded it, so I'll skip this step. But once it's downloaded, you'll cd into examples camera and then cd into OpenCV. And the file we're interested in is detect.py. And just before we run that, we'll double check the camera index. Yep, I've set my default to 2, so that should be okay. You'll obviously update your camera index to the right number. So we'll run this sudo python3 detect.py. So you can see it's doing object detection in OpenCV, and we're going to use this code and put it into PyQT5. Basically, we're going to copy the code from detect.py into anow.py. So let's open them up side by side in a Jupyter notebook. So that's sudo jupyter-notebook allow root. Awesome, we've got them side by side now. So let's start by copying the relevant libraries, which are going to be these 7 lines here. We already have OpenCV imported, so we actually won't need that, but let's just copy it in one go. And we'll paste it at the top there. And let's just quickly run this to see if we have all the relevant libraries. Okay, that seems to be working. But if you get a missing PyCoral library error, what you have to do is install that library with sudo apt-get install python3 pycoral. Let that do its thing. I've already got mine installed, so it's obviously not going to reinstall it. Cool, so the next step is to copy this slab of code from the main function into our initialize in the FrameGrabber class. And this is going to involve prefixing a lot of variables and stuff because we're using the self keyword. I don't do a whole lot of object-oriented programming either, so I'm probably going to do a lot of weird stuff in here. Now you'll notice that we're using this camera index argument here. And since we know our camera index, we can just substitute the default into 2. So let's just copy this across and put that in the bottom there. I think I've copied a few too many lines there, so I'll delete these 3. And perfect. Now, in terms of using an object detection model, I'm using my plates.tf Lite model. You can download this from my GitHub page along with the labels file plates.txt. I trained this model via transfer learning from the MobileNet SSD v2 Coco model, if my memory is correct. I fed this model over 400 images of Victorian license plates, so your mileage may vary if you're using my model. Anyway, you can sudo wget these files from GitHub, so that'll be sudo wget https github.com/educate/anow in capitals raw main plates.tf Lite, and to get the labels it'll be plates.txt, and then depending where you've downloaded the plates.tf Lite and plates.txt, you'll need to change the folder for your default model directory and default model. So I've kept mine in the previous folder in all models. And so that's where plates.tf Lite is. So if we did everything correctly, our app should still be working. So we'll go sudo python3 anal.py. Oops, I forgot to download the plates.txt file, so I'll just quickly do that. Sorry, that's plate_labels. And then we'll just need to rename that to plate_labels.txt to plates.txt. Awesome. So let's run our model again. So that's sudo python3 anal.py. Awesome, looks like everything's still working. So let's move on to the next slab of code that we have to copy, which are these 6 lines here. And we're going to paste them under if success. So we'll add a blank line underneath and paste that in. And I promise I'll explain all this in a tick. Then to make sure this all works when we run our script, we'll need to update all these parameters to self. Okay, coming back to this part where we added a blank line in between here, I wanted to add a space here because this one frame variable is actually being used for 2 different purposes. So it's being used for this and used for this. So what are these 2 things? So if I just start with this last section here, this is responsible for rendering the video onto our PyQT5 GUI. This is what we can see on the screen. You can either choose to pass an image or CV2IM again, and it'll show that on screen. Then this signal.emit section passes the image back to our UI main window class, which is then used in the update frame function. And so this top section here isn't being rendered on screen. But what's happening is that the frame variable is being written to this new CV2IM variable, which then converts it to RGB and resizes itself according to the inference size of my model, which is 300 by 300 pixels. Then this line performs the actual inference, and run inference is a separate class from the PyCoral library. GetObjects returns the top K number of objects detected in the model. The top K value is 3, so at any given time, there should be a maximum of 3 objects showing on the screen. And then this last line performs the inference. And copy the append objects to image function. We'll have to add self to the function parameters and add self to the function call. I think that should work, so let's quickly test it out to see if we've copied everything over correctly. And if we present it with a license plate just from my phone, awesome, that's detected it. So it looks like our inference is working. So just quickly breaking down this function here. So we're passing self and the CV2IM image, the inference size, the plates.tf Lite model, which is 300 by 300, and the list of detected objects and the labels. The next line is getting the height, the width, and the color channels from our CV2IM image, which should be 640 by 480 by 3 channels. So the scale will end up being 640, the width, divided by 300, and 480 divided by 300. So it'll blow the image up to 2.3 times 1.6 times. Then for each object detected, draw a scaled box around the object with the following X and Y, min and max Y coordinates. Then this provides a confidence level in percentage and the associated label of the object. Then we redraw the object with a rectangle with the following coordinates and then make this rectangle green. This is the RGB code. And then finally return the CV2IM image. So that's pretty cool right now, yeah? We've got our own app that performs inference on license plates on this tiny little device. Alright, we can close detect.py now, we won't need it anymore. And we'll just clean up a couple of these terminals here. The next thing we have to do is figure out a way to convert the license plate to text, and it's going to be a two-step approach. Now, the first issue we have is we're on our own now because we don't have any more code to steal from others. And the second issue is you can't convert a license plate to text on every video frame because if your video is 30 FPS, you'd be executing 30 checks every second and you'll probably crash the app or do a denial of service on whatever website or API you're using to check the plates. So the most sensible way I could think was to screenshot the green bounding box every 5 seconds. And how we're going to do that is by adding a new block of code at the bottom of this append objects to image function that takes the screenshot, and then we'll create a new function underneath it that calls that specific block of code every 5 seconds. Probably didn't make a whole lot of sense, so let's just jump straight into coding this whole thing. So what we'll do is create a new if statement here. So that says if take underscore photo. So let's start with the screenshot. I think the most practical name will be the now datetime. So we'll get that with self.now equals datetime.now string ftime, and we'll format it with year, month, day, hour, minute, second. And don't forget to import the datetime module. So right at the top, we'll add from datetime import datetime. Now, one thing to keep in mind is if our app picks up 3 license plates at a time and therefore screenshots all 3, they'll have the same file name, meaning only one plate will get saved because plate 2 would have overwritten plate 1 and plate 3 would have overwritten plate 2 because they all have the same name. So to get around this, what we'll do is add a number suffix to the file name by enumerating the for loop. So it gives us loop 1, loop 2, loop 3, and we can grab the number and put that into our file name. So in the for loop here, we'll update this to self.i, object, and we'll enumerate our list. And then our object file name will be obj file name equals fstring, and we'll go self.now hyphen self.i. So timestamp and the enumerated number, if that made any sense. And object path equals fstring.detected / object filename.jpg. So we're going to save it in the detected folder, and that's going to be the complete file name. Now, just to make sure that you've got that folder, yep, so I've got that there, and if you don't have it, it's going to be sudo make directory detected. And then we'll just add a print object file name, just so we can see what's happening in the terminal. Next, we'll specify the area that we want to screenshot, aka the region of interest, with self.roi equals cv2 underscore im, and that's going to be y0 to y1, comma x0 to x1. Then we're going to call the cv2.imWrite or ImageWrite function and provide a path of where we want to save it to and the region of interest. So that's going to be fstring. We're going to save it to the object path, and the area that we want to screenshot will be the ROI. And I've left a close bracket there. Awesome. Okay, so the code we've written here means it's going to be rapidly screenshotting because this is being called per frame. And again, if there's 30 frames per second, that's 30 screenshots per second, which will crash our app, and we don't want that. So what we'll do is add another parameter to our append objects to image function. It's called something like take photo boolean. And for the frame looping section here, we'll set this to false because we don't want it to screenshot every frame. Then finally, to make sure we only call this take photo block every 5 seconds, we'll create a new function underneath the append objects to image function. And we'll call it something like take underscore snapshot. And we'll call the self.append objects to image function with the same parameters as this one here, but we're going to set this to true instead so that it executes the take photo block of code. I kind of forgot to add self to CV2IM and objects, so I'm just going to be lazy and add these as global variables at the top. And then to call itself every 5 seconds, we'll use the threading timer library for a bit more optimization, which looks like this. This thread equals threading.timer 5 seconds self.take underscore snapshot thread.daemon equals true thread.start. Now we're setting the daemon to true because, well, if we don't, this thread and take snapshot function will keep running in the background even after we close our app. So by setting it to true, according to the Python 3 documentation, we can abruptly stop the thread when we close our app. Now this kind of suggests setting it to false and using an event to stop this thread is a more graceful way of doing things, but I can't be bothered figuring that out at this point, so we're probably doing a cheap and dirty way of stopping the thread, but oh well, it works. Next, we'll add a print. Just print take snapshot initialized, just so we can see in the terminal that this is working. And then we'll add a threading.timer to the initialize at the top. So just under inference size, we'll go threading.timer 5.0 self.take snapshot.start. And that's just to initialize the take snapshot at the start so we can kick off the self-looping function. I don't believe we need to set the daemon here because it's a once-off. Oops, and I haven't added the threading library at the top. So let's import that. So we'll run it again. And phew, everything's still working. Now, if you're getting this name error, name CV2IM is not defined, that's because your webcam is taking more than 5 seconds to load like mine. It's saying the CV2IM variable is being used before it's being declared. So we'll just update this initialize one to something like 10 seconds. So we'll save and run this again. All right, let's point some license plates at the camera. And awesome, that looks like it's taken a snapshot. So let's close and have a look at the detected folder. Now I use ImageMagick to open my images from terminal, and you can download that with sudo apt-get install ImageMagick with a K on the end. And then we can simply open the image with the display command. So let's have a look at the latest one there. 10.08.53.jpg. And look at that, there's our image, albeit with some unwanted blue text, but we can remove that in our code. So let's close this, and we'll just comment out the part where we've got the text. So that's this one here. We'll comment out the put text, and we probably don't need the % or the label. We've only got one object. We know it's a license plate, so we don't need that information as well. Now we need to convert the image to text, and we're going to do that with the OpenALPR library, which is an open source automatic license plate recognition library. This was a prerequisite, but if you don't have it installed, then just follow my OpenALPR installation tutorial. Link will be in the video description. OpenALPR is kind of like Tesseract OCR, but it's specifically for license plates. And I know that sounds kind of odd because if Tesseract OCR can do everything, surely you can read plates too, right? But look, hear me out for a sec. License plates have a lot of extra text on them. They've got like the state motto, some random emojis and whatnot. OpenALPR knows how to ignore these extra bits and do the optical character recognition, or the OCR, on the main parts of the plate, whereas Tesseract OCR will pick up all these extra unwanted bits. And that's why for a use case like this, you'd use OpenALPR over Tesseract OCR. So let's go back into Jupyter. So we'll leave ANAL open and then we'll navigate back to OpenALPR. We'll go to Source, Bindings, Python, and we're going to copy this code from test.py. That's the file we cloned from the OpenALPR Git repo. So as always, the first thing we'll do is import the relevant libraries, which is OpenALPR, and I think we've already got argument parser, so we won't need that. So we'll go back to the top of our script and import OpenALPR. Now we won't be using the rest of these parser variables for our code, so I won't be importing this whole slab. Then underneath our take snapshot function, we'll create a new function called something like def run underscore ALPR with the parameters self plate image, where plate image will be the file path of our saved screenshots. So we'll be passing in object path as an argument when we call this function. Next, we'll copy this ALPR equals none, and then these try and finally blocks. And we'll paste them in here and make sure we've got the right indentation. Then we'll update these placeholder arguments here. So my country is Australia, so I'll put in AU. And then for config and runtime data, you can copy that from the parser argument sections here. So this config one will copy that into here. And then for runtime data, we'll copy this here. Oops, I forgot to call the run ALPR function. So underneath where we've saved our file, we'll go self.run ALPR and we'll parse in the object path. Oops, so we're not using options.plateImage, we're just using plateImage. So we'll save that. So let's test that again. And there you go, it's processed that plate. Not 100% accurately, but that looks pretty good for a start. So it's processed our image to text and it returned the top 7 results or interpretations of that plate. Now let's break down what's happening here. At the top, we're just making an empty ALPR instance. It then does a check to see if ALPR is loaded properly. If it did, return the version number. If it didn't, then produce this error loading ALPR message. Then we set how many number plates we'd like returned, so the top 7 results, which is what we're seeing here, so that's the top 7 here. Then for default region, there is a WA in Australia, but I'm in Vic, so let me change that. You can find the region in the OpenALPR pattern file. Detect region, I believe that's an experimental feature, so they've left that as false for now. And then it opens the plate image file, and this line here, recognize array, is the member function of OpenALPR that does the conversion from image to text. So this is like, the one line of awesome code. And then the results are printed to the terminal, which is all down here. So let's go through that. The first for loop returns the top 7 interpretations of the plate without taking into account the state or pattern. So see, these are prefixed with hyphen, and then the second for loop factors in your pattern and prefixes those with a star. But for this instance, we didn't have anything starting with a star. Hopefully by updating this default region to Vic, we get something a bit more accurate. So the top result of this second loop is the plate that we want to check against the government website. And that's done a pretty good job. 87% confidence, and it got that right, but it didn't seem to pick up the template. So this brings us to the last function of the app, which is to write a post request or API call to a government website to check the status of that license plate or registration, or rego, as it's colloquially called in Melbourne. So we'll create a new function underneath run ALPR called def check rego with self and plate text as parameters. And here is where you'll write a post request or API call to a government website. Now, the one I wrote is obviously very specific to Victoria, Australia, and it's not going to be relevant for you. Like, my code won't even work in New South Wales or other states in Australia. So for now, let's just put a placeholder as print f-string plate text being checked. Now, when we call this function, again, we only want to check the top result that matches the pattern file. So what we'll do is create a new counter called j and put that underneath I, j equals 0 as well. Then inside the second for loop, inside the if block, we're going to write a check that says if j is equal to 0, in other words, the first plate with a matching template, call the check rego function. So that's self.check underscore rego candidate plate close bracket. And then we'll increment the j counter by 1. This way, only the top result gets sent to check rego, whilst the less accurate and less confident results won't. Oh, so it's picked up candidate, but I have misspelt it, so let's quickly update that candidate. Okay, come on, be nice to me. TTQ. Oh, awesome, there you go. So we've got the star there, which means it's matched a template. And then it's triggered the check rego function. So we've got TDQ being checked. Now, the final thing we have to code is writing our results to this table right here. I wrote the results to a CSV file and used pandas to output it to a table. Now, there's probably a more efficient way to do this without using pandas. So if you have any ideas, please let me know in the comments. But in any case, we need to install pandas first, so we'll sudo apt-get install python3 pandas. I think I've already got it installed, so that should be pretty quick. And also sudo apt-get install python3 numpy. Then we'll go back to the top and import it into our script. Import pandas as PD, import numpy as NP. So first off, let's create a CSV file called plates.csv. So back in our terminal, we'll type in sudo nano plates.csv. And since I had 3 columns in my table, I'll put 3 values in here, which are plate, rego, and sanctions. They're the 3 main things I care about. The plate number, and has the registration been paid, and are there any sanctions or fines on that plate. Paid rego and sanctions are the 2 main outputs from my government website. Obviously, yours will be different. So we'll exit with Control X and press Y to save. Then next in our Python script, we'll just do a basic file read and write in the check rego function. So that's going to be f equals open plates.csv, and we'll open that in append mode. And then we'll f.write f-string the plate text, and for now we'll just put some placeholder values like O and O just to say that everything's checked out with the registration and sanctions. Then we'll put a new line and then close that out. Actually, just being a bit paranoid, I think I need to put a new line there. Yep, there we go. Then we'll scroll down to our table here in Qt, and we'll write a function that refreshes the table, let's say, I don't know, every 5 seconds. So just in between update frame and retranslate UI, we'll type in def refresh underscore table, self, and we'll type in data frame equals pandas dot read CSV, and we'll read the plates CSV file. So we've imported the CSV file as a pandas data frame, and then we only want to return the first or last 15 results, whichever way you look at it. So that'll be data frame equals itself dot iloc or ilocation. So that's the last 15. And so that's sort index in reverse ascending order. So that'll be, I think, from latest to earliest. Then we'll write a for loop to go through each row in the data frame. So that'd be for each underscore row in the length or the range of the length of that data frame. And the code to assign variables to a Qt table is self.tablewidget.setItem each row, comma 0, comma QTable widget. That's QTable widget item df.iloc each row 0. So we're assigning column index 0 in the Qt table to column index 0 in the data frame. Then we'll just copy and paste this twice and update the numbers. And since we're using the QTable widget item, we'll need to import that too. So back at the top, we'll import PyQt widgets. So from PyQT5.qt widgets, import QTable widget item. And then right at the bottom, just above the sys.exit line, we'll create some space. And we're going to create a Qt timer. We won't need any threading for it this time. So it's just going to be timer equals QTimer, which means we'll have to import the QTimer library at the top. So that's from PyQT5.qtcore import QTimer. And then our final 2 lines of code will be timer.timeout.connect UI.refresh table and timer.start 5 seconds or 5,000 milliseconds. And that should be our app completed. How cool is that? Let's save it and test it out before we celebrate. All right, so hopefully this posts it to the table. Fantastic, look at that. There it is, it's populating our table. That's pretty cool. And we're pretty much done with the coding side of things. How cool is that? We're done. We've got a full functioning, working license plate detection system app called ANPR. I'm blown away that it's working. How cool is that?
Now onto the car installation, where we'll need a 3 to 5 meter USB cable, a 12 to 18 volt battery pack, and a car. For a small hatch, a 3 meter cable was long enough, but if you can get 4 to 5 meters, that might be safer just to give yourself some leeway. Now what you're going to be doing with this cable is routing it from the front of your car through the side of the engine bay, and depending on your car, you'll feed it into a hole or a grommet, which then goes into the cabin. If it's a hole, like this car, you can feed it through pretty easily and it ends up routing through the side panel and into the cabin. This method isn't great because the cable is a little exposed to the outside of the cabin, but installation is so much easier. On the flip side, if you're routing it through a grommet like this, it'll usually end up behind the glove compartment, which is more secure because there's no cable being exposed to the outside of the car. But installation is much harder because that grommet is super tight and it feels like it doesn't budge. If it's your first time doing it, I promise you're gonna end up cursing and swearing at your car because it'll feel impossible to route that cable through, but I promise it's doable. Once that cable is fed through, you want to mount your camera to the front of your car. I used one of these camera mounts from smallrig.com and found a safe spot to mount it that wasn't going to crack my bumper or grille. Once you've got that camera connected to the long USB cable, we'll pop back into the car where you'll need your Tinker Edge T and a 12 to 18 volt battery pack to power it. For visuals, I got this portable monitor off Amazon, which you can power from the Siggy lighter. Put that all together and you've got a complete ANAL system in your car. Now you can cruise the streets feeling like a police car, scanning everyone's license plates.
That's it for this video, which was a huge effort to put together. I hope you got something out of it. The only loose end I think I left was my plates.tf Lite model. I didn't explain how to train your own model so you can tailor it for your own object detection. I use transfer learning and I'll do a video of that in the future, so please subscribe so you don't miss that when it's released. Thanks for watching, happy coding, happy driving, and I'll catch you in the next one. See you later.